Well, welcome everybody to today's class for the Maine Masonic College. Let me just quickly explain a little bit here about the Maine Masonic College. Since its founding in 2005, the Maine Masonic College has worked on developing qualified faculty to share their personal expertise and their dedication to learning. It's the college's goal to offer 2 classes a month free of charge, with the majority of these classes open to the general public. In addition, there are the 2 semi-annual events. One is the Celebration of the Arts and Sciences. The second one would be the College Convocation. And at each of these, we feature prominent guest speakers who are leaders in their fields. The college also, in addition, I don't know if everybody knows this, but we've developed strong educational partnerships outside of the craft also, specifically with the University of Maine Honors Program, and we engage with them every year. They have been guest speakers many times at our events. We also support the UMaine Planetarium, and in the past have held events there, and I'm sure we will again. We take part in National History Day, and we provide some financial support and volunteer hours to youth betterment initiatives, particularly outside of the UMaine system into the high schools. And we are really just trying to kind of, as a group, support that love for learning across all ages. So one of the things is, as Masons, we know from our ritual about the importance of studying the 7 liberal arts and sciences. And although these were traditionally grammar, rhetoric, logic, arithmetic, geometry, music, and astronomy, in the modern world, they've really come to encompass a couple of other specializations like humanities, social sciences, and performing and fine arts as well. It's from that broad foundation that the Masonic College tries to create our programs, which usually include topics of interest to anybody with an inquisitive mind, whether you're a Freemason or not. So the classes sometimes may be limited to Masons. We would always make that clear ahead of time. It might make reference to lessons we might have learned in the craft, but it is also our goal to academically engage with anybody in the general public, particularly just to kind of, get a better understanding. The college motto states, and you will see it later, that to bring more light is what we try to do. And we try to do that to everybody that we meet. First off, thank you for attending this particular course. And I would like to toss it over now to our instructor, Dean Luke Shorty.
Thank you very, very much, Mr. Chair. Good morning, everybody. Glad to see so many people from all over the world here joining our course this morning. My name is Luke Shorty. I am a Mason from Limestone Lodge number 214, which is in far northern Maine, though I live in a small town in central Maine called Winthrop, and I work in a small village in the forest called Lee. So I'm really all over the state of Maine. I work at Lee Academy, which has campuses both in Maine, Shanghai, China, and Daegu, South Korea. Prior to being the dean of the Maine Masonic College, I actually taught mathematics, and my formal training is in mathematics. And so today we're going to talk a little bit about geometry, and this truly is an introduction to geometry. So if you're already ready to, construct the golden ratio and construct regular pentagons and things like, good, I see a compass and a straight edge there. That's wonderful. If you're ready to do stuff like that, that would actually potentially be the next course. What we're going to talk about, let me talk about the goals of what we're going to go over. For those of you who might not have seen geometry since high school, or may not have seen much of geometry at all, this will be a good introductory course. We'll talk about the objects that we play around with in compass and straight edge construction. We'll talk about how to duplicate and divide angles and segments. We'll talk about how to actually construct parallels and perpendiculars, which in our Masonic lectures, we know have significance. So as we go through this, we'll sprinkle in some allegory or some connections to our Masonic ritual. From there, we'll talk about, if time allows, how to construct regular polygons, at least the simpler regular polygons. We won't get to the pentagon because that involves constructing the golden ratio, which I intend to hopefully have a course on that as well in the future. And so those are the goals of today's course. Now, usually when I run this course, we run it in person, and we bring a whole bunch of straight edges and compasses for our students and our participants to use so that they can try out and they can be active. Well, it's hard to do when we're all in different locations. But if you do have a compass and straight edge, awesome. Feel free to show that in your screen. I saw Frank had his. Looks like Dave's got his. So does Bob. Wonderful, wonderful. So if you don't worry about it. You could, if you wanted. Oh, good. Gary's got one there. If you don't, there are some things you could makeshift and do it at home, or there is a digital solution. That digital solution is a piece of software called GeoGebra, GeoGebra. And there will be two ways in which you can participate. You can participate passively and follow along as I share the screen and kind of go through the course that I've created there. Or if you're feeling comfortable, technologically speaking, I will share a link in the chat window that you can click on, and that will give you access to the course on GeoGebra, and you will be able to kind of play along and follow along as well digitally. And so it allows you to simulate a compass and a straight edge in our constructions. Are there any questions before we dive in? Okay, so we're going to dive in here, and before we do, I just want to thank you very much for your patience, because we are in a grand educational experiment right now and trying to have hands-on instruction and learning while also doing it remote in different modalities. So thank you very much for your patience. Who's ready to learn some geometry? Just wave it. Good, I see some thumbs up, some waves, good stuff. So let us begin. I'll begin here by sharing my screen. Here we go. So now you should be seeing, well, what says Zoom actually, but really, let me go to the right page here. So I'm going to go over here to GeoGebra, and there's a course that I am running. Now I've made it so I can't really actually see folks in there. So if you do have a question, either holler it out or type it in the chat window, and we'll get to it that way. And so what I'm going to do is I'm going to share this link. I'm going to copy this link, and you're going to see it in the chat window of your Zoom window for those of you who want to try to participate by joining in. After we do that and people try to get in, what I will do is I will then start the course, and those who want to just kind of follow along from home can do so. So in your chat window now, you should see a link. It says https://www.geogebra.org/classroom/a series of characters. And if you click on that, that should allow you to join. And look at that, Ranesh has joined. Dan has joined, welcome. Brian is in, wonderful. And with that, I believe, good, people are able to get in, that's wonderful. Welcome aboard. On the left-hand side of the classroom, what you can see here is you can see a class overview. These links allow you to process through the class that we're going to do here in 2 hours. I'm hoping that I've condensed it enough so we can get through all of this in 2 hours while also taking questions and not losing anybody. So we'll see how well we did on that. And we'll take the lessons we learn in today's class, and we'll learn from them and make the next time that we offer this class even better as we go through. So now that folks are on, let's go and click on the class here. So, I want to actually be in the class. This is my first time using this software. And so one of the things that I can do, let me go back to GeoGebra. Now that people are in there and they have that, I'm going to go to, not the classroom. resources. I'm signed in as me under my profile. And really what we're doing is we're going to walk through this introduction to geometry. So everyone should see this front page. If you click on introduction to geometry, it's going to lead us to some tasks. It's a very beginner level course about compasses and straight edges and how to construct different shapes. The first thing we have to do in engaging in any geometry is to understand what those working tools are. So let's talk about that. In classical geometric construction, there are two tools, the compass and the straight edge. And there's a task here called compass and straight edge tools, and it will allow us to walk through on how GeoGebra works. For those of you who actually have compasses and straight edges, you can actually follow along as well. So the way this worksheet works is you have tools up here in the top menu bar, and you have arrows that will let you go back, undo, or redo, zoom in, and some other options here. When we do geometry, it's about points, lines, angles, and from those we can make different shapes, different forms. And so if you're at home, feel free to put a point on your paper. That's just taking your pencil and making a little dot there. That's pretty cool. All right, nice. If you're on GeoGebra, all you got to do is click. Let's make a second dot or a second point. With 2 points, we can make a line. So a line in geometry is one that goes on forever in either direction. This is what the straight edge is used for. The straight edge is to just make straight lines. If you have a ruler, you aren't supposed to be able to use the tick marks to measure distance. Your tool that you use for measuring is actually your compass. A compass is used to measure. And in that measurement, it makes circles. And we'll talk about that in a second. So this is a line, just so we're very familiar with the vocabulary. Lines that don't go on forever in either directions is called a segment. A segment is a finite line. It's just a snippet from a line. And last, if I have 2 points, which you can do again, use your pencil if you're at home to make 2 points, you can make a ray. An array is like a line, except it goes off infinitely in one direction. Okay, so those are the 3 straight line tools that our vocabulary will be using in today's course, right? You've got lines, go on forever in either direction, segments, which are finite in either direction, they have a set length, and rays, which go on forever in one direction. Is there any question about those terms at this point in time? Hearing none. Other actions that will be important in this course is we're going to have to be able to find intersections. If you're at home, it's very easy. You look at the piece of paper in front of you and you'll put a dot where the 2 objects intersect. In GeoGebra, you can have this drop-down menu that says intersect, and you pick the 2 objects, this line and this ray, and we'll put the point there where they intersect. And so that is lines, segments, rays, and intersection. Okay, I'm now going to undo a whole bunch of this, and I'm going to talk about the compass next. Any questions? Hearing none. And it's okay to ask questions. This is the beginner's course. This is where you can ask any crazy question you'd like that has to do with geometry. So, a compass. What does a compass do? A compass is a measure of length. It's a way to measure a length and keep that length fixed. It doesn't really measure in units, right? Your compass doesn't be like, oh, this measurement is 5 inches or 6 feet or 5,280 feet, which is a mile. It doesn't do that. It measures in units of compass length. It just says, okay, here's a fixed length, and I can copy that in places. So for example, if I had 2 points, with your compass at home, you're going to put 1 point, usually the sharp pointy end, at one location. In the lead, in another location, and it forms a circle, right? It forms a length. And forming that length, you now can make a circle of that length. Usually if it's at your pointy end, you'll have a circle that looks like this. In GeoGebra, what you can do is you can say, hey, I want to measure a length. It's going to give you a circle because all of the points on that circle are equidistant from the circumpunct. That's what the center dot is called, is the circumpunct. Perhaps you've also heard about that in our lectures. And so that circumpunct is where the pointy end goes. The circle that's drawn is equidistant from that point. And so I can measure that distance all around a given point. And I could put that anywhere I want in GeoGebra. You can measure that distance, pick your compass up because your compass won't lose that length, and draw a circle anywhere else on your paper, okay? And that's all the compass does. It looks more fancy than the straight edge, but really its job is to maintain and hold length, right? So if you didn't have a fancy compass at home that you can open and close, you could use a piece of dental floss in a thumbtack and wrap it around a pen and hold it real tight, and you'd be able to do the same thing. And that's what is the most amazing and beautiful thing about geometric constructions. And the elegance of it is how simple these tools are. And from these simple tools, what we are able to construct and deduce and create, it's beautiful. It's like poetry in motion. One last thing that we're going to do to prove that certain things are parallel or perpendicular is the measurement of angles. And so I saw one of our brothers has a protractor. Way to go. That will help you measure angles. For those of you at home, it may be a little difficult, but for those of you playing the electronic version, you can do the following. You can select 3 points to create an angle. And so in GeoGebra, you always want to go clockwise. So if I wanted to find this angle between A, C, and B, those points, I would actually start at B and go clockwise, B, C, A, and it will measure that angle, which is 19.36. Another beautiful thing about GeoGebra is I can move things dynamically, which is harder to do on paper, right? I can move things around and it will move with me. So if you're playing at home, great, keep it up. You'll have access to this link and to this course afterwards, so you can play around with GeoGebra at your own leisure. You can measure angles, and also measuring distances will help us determine if something is equilateral or if it is a regular polygon of some type. Regular means equal sides, equal angles, and we'll talk a little bit more about that. So that's the overview of the compass and straight edge tools. Any questions about that? I'm going to go to the gallery view just to see if I see any confused faces. Can we give me some thumbs up if you're feeling good so far? Good, everyone's feeling good? Perfect.
Can I ask a quick question, Luke, actually?
Yes.
How did geometry make the jump here from two-dimensional constructs like this to actually being able to, it can calculate mass, I'm assuming, right?
Not with a straight edge and a compass, you can't calculate mass, but you could calculate mass. I mean, for example, how does the saying go? From a point to a line, from a line to a superficies, to a superficies to a solid. With it, you can construct and deduce plots of land. In the longer course, the 3-hour course, we actually talk about specific angles, special angles like 30 degrees, 45 degrees, 60s, and 90s, which are easy to construct, and you see a lot in architecture. But from that comes the Pythagorean theorem. And the Pythagorean theorem, believe it or not, is actually a theorem about area. For those of you who are familiar with our Masonic lessons, the 47th, 45th, whatever that problem of Euclid is, 47th, thank you, brother. The 47th problem of Euclid is about area. It looks like triangles because you're talking about edges, but you're talking about squares, which then starts getting you into area, and it really builds up similar to how the lecture is, from a point to a line to a superficies to a solid. Because when you can start talking about area, you can talk about the base of something. And you can then talk about measuring length of stuff on compasses, which would allow you to stand up perpendiculars. And so you can bring it into that other dimension. We won't get there today, but as we develop these geometry courses in this geometry series, these will be things that will be guiding my process. I see we got a question over here by a brother, I don't see his name, but of my upper left-hand corner.
Brother Yates?
Yeah,
Yes.
just a quick question. AB is 9.51. 9.51 what?
Great question. 9.51 in GeoGebra, there is a way to check out your units. Very good question, Brother Yates. Let me see if I can figure out. Right here, it says it's in centimeters. So I guess that's using the units centimeters here. And I know there's a way to change it in GeoGebra. If you were using it for like, hi, I'd like to map out my living room and I need to have appropriate units, you can change those units in GeoGebra. Great question.
Right now, it just looks like about 1.5 inches. You know?
Right. On the screen, I'm sure that's not 9.51 centimeters on my screen, but to the program, that's what it's measuring it as.
Thank you.
Great question. Other thoughts and comments? All right, let's do some construction. I like the dudes who are at home who are doing it on paper and pencil. Thumbs up to you. Old school's the way to go. I like that. So here we go. The next part of this chapter of understanding the working tools is basic constructions. And I want to give credit where credit is due. Sandra Miller in GeoGebra, they have all these classroom resources where teachers and math instructors and engineers have developed a bunch of these little programs and tools to play in. And Sandra Miller is one of the many that I'll be giving credit to in this course for creating some of these. And it's basically along the lines of things that I do in the in-person course. So there are a couple of constructions we're going to do. We're going to do 4 of them. And the angles can be tricky for some people, and that's okay, especially if you're new to geometry. There is no dumb question. If you are lost, feel free to ask. Feel free to hop in and ask. We're here as brothers to support each other. That's one of the things about Freemasonry, right? It's the cement that holds us together as living stone in the craft that we are about. And so what makes that cement stronger is when we ask, hey, I need help. I don't quite understand this. Because odds are there's probably someone else who feels the same way. So we're going to do 4 simple constructions. How am I doing on time? I'm doing all right. We're going to copy a segment. How do I copy a segment? I'm going to bisect a segment, which means cut it in half. Bisect is funny talk for cut it in half. We're going to copy an angle, and we're going to bisect an angle. And if you can copy an angle, you can double an angle. If you can copy a segment, you can double a segment. Now, remember, we only have 2 tools with us. As we see here, we can make lines and we can measure distances with a compass. And so I've got this segment AB, and Miss Miller has, like when you select it, she has a little thing here. You can click on help if you don't know how to use that tool. So if I need to create a segment, segments have a certain length. I only have 1 tool that allows me to measure length. Somebody shout it out. What is that tool? Is it the straight edge or the compass that measures length? Don't be shy.
It's the compasses.
It is the compasses, right? So we're going to use the compasses to measure length. So if I take this compass and I measure this length, I now know that the radius of this circle is the same length as segment AB. I'm going to zoom out here, so I'm just zooming out. It makes it look like that's getting smaller, but I'm just zooming out, okay? So I'm going to zoom out. I'm going to put this circle wherever I want. So those of you with a compass and straight edge, go ahead, measure that segment, put your circumpunct down there, draw me a circle. Now, if I want to make this segment, all I have to do is pick a point on that circle. I don't care where it is, I'll put it right there. And then I draw a segment from the center to that point. And lo and behold, it's as simple as that. You move that point wherever, I guarantee you, let's measure the distance. The distance from this point to this point, we'll call it C and D, and the distance from this point to this point are both 4.18. And so regardless, and if I change that distance, again, GeoGebra is dynamic. If I change that distance, this method will continue to produce the same length. And it's just that easy to double or to create a segment. That's how you copy a segment. Super easy. Any questions on that? Anyone like, oh gosh, I stabbed myself with the pointy end. Help, I'm bleeding. So, all right, let me undo all of this and then just show you how to double it. How do I double it? Super easy. Again, we're going to use the compass because the compass measures length. And I'm going to take it and I'm going to put it right on B, or A for all I care about. And I'll take a straight edge and I'll just make a straight line all the way through A and B. I know that it now intersects the circle here. And now I know that this segment from A to the other end of the circle is twice. It's the diameter now of that circle. So that's how you would double a segment, 4.18. And this better be 9.36. 8.36. Man, I taught math and I can't multiply. Whew. So there you have it. That's an easy way to double a length, right? Now, if you think about this and you were out in the field somewhere, you can still make a large compass, nail something into the ground, and then have a piece of rope with a stick and keep that taut and measure it out. So you can use these skills, even though you're doing it on paper, you can use it practically in the real world. Any questions on copying a segment? I'll give about 5 seconds of pause time. Hearing none, we're going to move on to bisecting a segment. It says, how the heck am I going to cut this thing in half? And you're about to see a geometric construction that is going to be very important to us. It's called the visica piscis, and we'll talk about what that is later on in the course, but not in this segment. I want to cut this in half, right? Again, I have to measure something. And when it comes to measuring something, cutting in half, doubling, measuring a length, what tool do I use? Somebody else who hasn't spoken yet. What am I going to use? Straight edge or a compass?
Compass.
That's right, the compass. We're going to use the compasses. So somehow I need to use the compasses to cut this in half. Now, another way to use a compass is you can pick a center point and then move a radius out. It's easier to do on that compass you have on the paper. If I were to find the middle of this object, what can you tell me about if I had a circle around this end and a circle around this end? And notice they aren't on that line, but if those circles were to meet in the middle, how often would they touch? Where would they touch? Once, twice, 3 times? How many times would those two circles touch if they were right in the middle?
1 point.
That's right. They touch in 1 point. But get this. If I make, don't want to use the compass anymore. If you're in GeoGebra, make sure you pick the right tool. So I'm going to go back to moving. So if I take them and I move this circle, I make it a little bigger, and I make this one a little bigger than half. If I make them bigger than half, they're going to touch in how many points? How many points do these circles touch? How many times do they intersect? 1, 2, or 3, or right now it's none. If it was right in the middle, it would be 1. But if it's bigger, it's how many?
Twice.
2.
Twice, exactly. So now I have 2 circles that intersect. If you have a compass at home, make the circle that big enough so you know that it's gone beyond the halfway point. Okay, so make these 2 circles so it goes beyond the halfway point. And we're going to just take a line And we're gonna, well, first we're gonna put points where those two objects intersect, right? So you've made two circles, they intersect in two places, put 2 points there. Now we're gonna take a line and we're gonna drop that line right through those 2 points. That's what your straight edge is for. It's to draw lines. And so now I've drawn this line that connects those two intersecting points. And I conject, I make the statement that that line has cut that segment in half. How can I check? Well, let's make an intersection point between this and this. There's that dot right there, and I can measure it. The distance between here and here is 3.67, and the distance between here and here was 3.69.
That only works if the two circles are the same size.
Aha! Good statement. Wonderful. So that's right. We need them to be the same size. I didn't make them the same size. How can I make them the same size? If you're at home, don't change the length of your compass. If you're on GeoGebra, this is how you can do it. Make your circle, go above and beyond, and then change it to the compass and say, I want it to be this fixed length and center it here. Now that you've done that, if I move these, I know the circles are going to be the same length now. Very good. So now that I know they're the same length, where do they intersect? They intersect here, in here, and we're going to drop a line down. Where do they intersect? I want the intersection of these 2 points. And let's make sure that it truly does cut it in half. 3.68. And this better be 3.68. And it is. And that is absolutely the key. Brother Yates, correct? Awesome. Brother Yates hit the nail on the head. They have to be the same amount. Now, it is true that I did forget that, but there will be times in this course that I will do that intentionally to help stir dialogue, to be like, what did we do wrong? What's wrong? Let's think about this. Because I feel that we learn best when we engage. And sometimes it's good to engage when things don't work out the way we thought that they would. So, great example of that. So thank you for that, Brother Yates. Any questions on bisecting this segment? I'll give 5 seconds of thought time. Still feeling good? Show me on a scale of 1 through 5 how you're feeling. 5 means I'm feeling great. 1 is like, I am in the wrong course and I'm going to log out. Good. I'm seeing some 5s. Good, good, good. Perfect. Wonderful.
Brings back high school memories.
Yes, hopefully good ones. And if not, hopefully I can turn them into pleasant memories. So I want to show you one more thing. This is just a sneak peek. If I took the length of this circle and I put it on B, pardon me, if I put it on, it's a little past B. If I put it on B, looks something like that. This is a shape that we're going to talk about later on in the class called the Visica Piscis. It's easy to make because basically you just take your compass, make it the length of the segment, make a circle around a point, take that point, go to the other end and do the same thing. But this is going to be very important in certain constructions. And if there are members of the York Rite, if we have time, I'll show you what my master's mark is because I did it using geometric construction. So that will be later on. So that is how you cut an angle in half. And if you can cut an angle, not an angle, that's how you cut a segment in half. And if you can cut a segment in half, you can cut it into what?
Quarters.
I can cut it into quarters, cut it in half again. And so you can divide by 2 now. Wow, there's a way to use geometry to do division by 2 or multiplication by 2. Great. Now, angles are a little tricky. And first, let's measure this angle. And remember, GeoGebra measures angles clockwise. So I know that this angle here is 63.67. Okay. Make it, there it is, 63.67. If I want to measure an angle, again, I'm talking about measures. If I'm talking about measures, what am I going to use? Everyone should be shouting it at the same time now.
Compass.
That's right.
Compass.
Measurement, use a compass. Want to measure that? Use a compass. Wife says, how long is that table? Hand her a compass. So, anywho, let's copy this this angle. In order to do so, first I'm at least going to need a line because angles come off from lines, but I'm actually going to make it a ray so we don't get confused. So I'm going to make a ray right here. Okay. Now, in order for me to make this angle, I need to measure a certain length. So if you've made an angle on your piece of paper, pick one of those legs of the angle and put a dot on it. Okay. From that dot, you're going to measure that length with your compass. Okay. And you're going to move that and you're going to put that right over here where you want to copy the angle. So again, I'm going to do this just so it's clear which thing I've copied. I'm taking that angle this circle right here, and I'm just picking it up and putting it on this ray. Okay. So I've just taken it and I've put it on this ray, same circle, because now it tells me, hey, this intersection right here, is the same as that point right there. I just copied it over. Great. Now, what I'm going to do is I'm going to mark out here where it intersects the other leg. Okay, so I've marked out where that exists and lives. And then I'm going to take my compass and I'm going to measure this length right here. Okay, oh, look at that. So I know the circle around this point is going to intersect that other circle in the same area. So if I've done that, I see where they intersect at home, put a dot there. And then take a ray and put it through there. Now, if I measure this angle, it should be 63.67. Let's see if that's the case. Remember, clockwise in GeoGebra, 63.67. And that's how you copy an angle. Let me do it just one more time very quickly for those of you who are like, whoa, that was magic. I'm given an angle. I'll create a little ray of where I want to copy it. I don't care which direction it's pointing in. You know, heck, point it down this way for all I care. Wherever you want to put it on your paper, put it there. If you've already copied it once, feel free to do a second one and follow along. We learn better through repetition and through practice. So now, in order to actually copy this angle, I need to put a point on one of the legs of the angle I want to copy. In that, I will make a circle. I will measure the length between those two, and I will make that length. I'll put that circle on where I want to start that other angle. Now, this next part is important. It's good to have that circle there as well, because I need to find out where this circle intersects my other leg. It intersects my other leg right there. And now I'm going to take my compass and I'm going to do a second measurement. I'm going to measure from this point to this point. Got another circle, and I'm going to put that right there. In doing that, I know that they intersect right here. And all I have to do now is make a ray right there. And this should give me that measure. Remember, clockwise of 63.67. So let's prove it by moving this thing around. Oh, look, good. I made it really large. What? Oh, somebody tell me what's going on here. It was working great until I got 180. Something happened when I hit 180. Can anybody tell me what's happening? This is a good question. Anyone got any thoughts on it?
Inverted angle?
Yes. Notice if I add, I'm going to make this one 300 just to make the math easy. Close to 300. If I add 300.7 plus 59.3, what do I get? I get 360. It's how this thing was constructed. So this works really well in copying angles that are less than 180. So it will copy any angle less than 180. How are we doing? Anybody confused? Could I get a 1 through 5 to see how people are doing again? Are we still feeling good at 5s? Good. I like the honesty. I got a shaky hand over there. That's good. Be honest with us here. How are our friends doing who are doing this virtually? Are you feeling good? Do we have any questions or comments in the chat window?
We're doing good so far.
We're doing good so far. Good, good. And if you're on the chat, feel free to do a 1 through 5. I'm glad people are feeling good. How am I doing? Good. We're doing good pacing wise.
Yeah,
This is my
look, I
first
think I
time-
need to get, look, Reneesh here, I think I need to get a hang of using GeoGebra.
Yes, and that will come with practice. That will definitely
Yeah.
come with practice, brother. So practice with it, play around with it. It will get better and it will get easier. And they even have ones that will walk you through step by step. So when you have that opportunity, that will be right there to take that and help you out. Good. So we're
It's
copying
fun.
the name.
It's
Go ahead.
very fun.
It is very fun. I agree. So next one is bisecting an angle. Because guess what? Actually, can anyone see how I would double an angle? If I can copy an angle, how would I double it? Let me just show you that real quick, because doubling an angle is equally important, right? If you're somewhere and you got to double an angle to go from a 30 to a 60 or a 45 to a 90, let me show you how to do that. It's similar, except I'm going to use this leg right here as the leg of my other angle. So real quick, we're going to put a point here. I'm going to make my compass. I'm going to go a little quicker because I'm feeling people felt they were comfortable. Boom. That makes that. Let's find out where it intersects. It intersects right here. All right. So if it intersects right there, first I'm going to put my circle on the point where I want to make my angle. Guess what? It's the same circle. How exciting. So I'm going to take a compass. I'm going to measure this length and I'm going to put that right here. And now I'm going to say, where does this circle intersect this circle? And it's going to have that point right there. And I'm going to take this and I'm going to make a ray. And now I've doubled that angle like magic, right? Let's prove it. Let's measure some angles. So we want to go clockwise. Okay, so that would be from this to this to this, and from this to, nope, I knew that was the wrong way. Hold on. From this to this to this. That's the one I want? Oh no, I want to measure the angle. There we go. I'm glad that you guys get to see me make mistakes and play around with this. But yes, they are the same. 6367, 6367. Easy to copy an angle and double it. The harder question is, how do you cut an angle in half? Let's take a gander, shall we? Here we are. We're going to bisect an angle. So I want to cut this angle in half. There is a way to do it. First and foremost, I'm going to want to put, let's make sure, because there's going to be an issue if I don't do, I'm wondering if I should go down the same rabbit hole that Brother Yates did earlier. I'm not going to actually. Let's do the following. We're going to do a measure. So guess what I have to use? I have to use a, oh, come on, guys. Starts with a C, rhymes with rumpus.
Compasses.
Yes, we're going to use a compass. So I'm just going to take a compass that's going to be centered at that angle, move it out a certain distance with your compass, click right there, and I know that it intersects. I'm going to put points where it intersects the angle, okay? When I've done that, I'm going to create a line that connects those 2 points. So at home, if you want, make your circle, mark those points, drop a line. It almost looks like an eyeball, doesn't it? And now what I need to do is, I bet if I cut this segment in half, I will also cut this angle in half. Do we know how to cut a segment in half? You bet your sweet bippy we do. So I'm going to take a compass. I'm going to measure that length. I'm going to measure that length this way. And I'm going to find out, where do those 2 circles intersect? I want this circle intersecting with that circle. And I know it's here at my angle, and it's here over here. Again, it's that vesica picus, which stands Latin for bladder fish or fish bladder. We'll talk a little bit that later. But if I take that and I take this line and I draw a line connecting those 2, I bet I have cut that angle in half. Let's find out. 1, 2, 3, 30.31. 1, 2, 3, 30.31. Was that other angle 60.62? I know it's hard to see now that I wrote those other ones, but hold on, let me do this. I want to move. I'm going to just move my angle here, make my angle a little bigger. So 72, 72, and I think that is 144.18. I can't move maybe I can zoom into it, and now it's going to stay clustered like that. But it does, it cuts it in half. So that is how you cut an angle in half, and it doesn't matter. I showed you it doesn't matter by moving these pieces around and changing that angle. Again, if I go past 180, does it get wonky? Yeah, it gets a little wonky, but it still cuts that angle in half, right? 120, 130, 130, and 260. So it will still cut that in half. It's just pointing in the other direction. So this ability to cut an angle in half is powerful. If you have a 90-degree angle, something that is a perpendicular, and you cut that angle in half, regardless if it's 3-dimensional or not, you'll now have a 45-degree angle. You could make a joist if you wanted to. Any thoughts or questions on that? How are we feeling about the bisection of an angle? Not the overall, just this activity. Are people feeling at 5s with the bisection? Good, good, awesome. And if you aren't, that's okay. This is a beginner's course. That's why we got you here. Any questions before we move to parallels and perpendiculars?
Is there any way? There is really no other way to make sure that a measurement is completely accurate except for doing something like this, right? Based on
That is correct.
the circle. The circle is probably the ultimate form of accurate measurement.
I can say with confidence that the compass was the first ability of taking measurement. If you think about a fixed rod, even a fixed rod, right? Let's use this pen right here. This pen is a fixed rod, but really what it is, it's a rusty compass. It's a compass that doesn't open or close. It's a compass at a fixed level. You slam this piece of the pen into something, the fixed length, and you move it around, you're making a circle. It's a rusty compass that can't open. And that, I'm confident, is man's first measurement. And because of that, it's amazing what you can build by being able to measure and mark out fixed distances. I mean, I don't want to get too crazy or too elegant or too wild, but I really do believe it is the foundation on which a lot of our innovation, engineering, and parts of our society and agriculture fall from, is our ability to measure.
And this is all the basis of surveying, really. Just the simple beginnings here is the surveying.
Yeah, we're playing around right now with points and lines. And then at the end, we'll get to superficies. And then from there, we'll probably have one on solids. I will say one thing, just as a trivia. So if you're feeling lost, don't go down this rabbit hole. You can plug your ears if you want. All of this stuff works only in Euclidean space, which is flat surfaces. If you go onto a sphere or a hyperbolic space, and we can explain what that is in perhaps the non-Euclidean Maine Masonic course, things break down and they don't work the way that that you think that they would work. So we won't talk about that here today. But if people are interested, I could do a course on the geometry on a sphere or the geometry on hyperbolic space, which is mind-blowing. So with that being said, any other thoughts, questions, or comments before we start talking about parallels and perpendiculars? No? All righty. Here we go. Parallel lines and perpendiculars. And I apologize for those of you who are actually in the course. I'm not following along on how you're doing in the course. The courses seem to be made to be asynchronous, which means you can do them at your own time. I'm using it to demonstrate in real time, and I'm hoping you're following along online on GeoGebra. So we're going to talk about how to construct parallel lines and perpendicular lines. Somebody tell me, what are two parallel lines? What's the definition of parallel lines? Feel free to shout something out if you think you know it, or type it out.
Two lines that never intersect.
Two lines that never intersect. That is a great definition on Euclidean space. Those two lines never intersect. I got two lines, they're parallel, they go on forever. Remember, lines go on into the infinite. They'll never intersect. And so we're going to talk about how to construct parallel lines. And we actually have already done some perpendicular constructions as well. But there are a couple of ways of doing that. So parallel line construction. This is by author named Tim, a Polish name I don't know how to pronounce, Brzezinski, I believe. And he has a model here asking us to construct a parallel line through a point P. So it has to be parallel to this. And one of the ways of doing that, if two lines never meet and you draw a line through them, what can you tell me about the angles let me see if I can draw you a picture actually. If I did have parallel lines, can I actually just throw one on here? There are tools that would allow you to cheat, but he did not put him in here. Good guy, Tim. If I were to draw a line that connects, say, this dot here to point P, and I had a parallel line, just bear with me, say this line was parallel to this line. This angle right here would be the same as this angle right here. Do you see how that would be the case? That the angle between these two would be the same as this angle right here. And that's how I'm going to prove something is parallel. I'm going to undo that line. I've connected these two. Do I have a way of creating angles? If I was given an angle, did we learn a method that would allow us to create an angle? Heck yeah, we did. I can copy that angle now. So let's go ahead and copy that angle. And I'm going to copy that angle off from this line I made right here. Okay, so I've got two lines. I'm going to copy an angle. To copy an angle, I need to put a point. I'm going to put a point here on this line, on this object right here. So put a point on this first line that you're going to make a parallel of. And to copy, what do? We take a compass. And I pick 2 points. And I make that length right there. And I say, where does that line intersect? Right there. I'm going to take that same circle that I made. I'm going to put it up here on P. Okay. Now, on P, I'm going to take a circle. I'm going to measure the length between this point and this point. And I'm going to put it right there on that And now I see where these two things intersect, and I will make a line between this point and that intersection point. And lo and behold, I have created two parallel lines. Questions on that? None, okay. So how do I prove it? I measure the angles, and proof is in the pudding, as they say. So what is this angle measure? That's 57.2. 57.2. They're parallel. Now let's do a little piece of Masonic fun before we move on to the next one. It is possible to make a, well, actually, let's make the perpendicular bisector next. So let's go to the next one. Unless there are questions on how to construct that parallel. Did everybody have some success in doing that? Good. I'm going too quick, holler at me. Otherwise, I'm going to start picking up the steam. Perpendicular bisectors. A perpendicular bisector, bisect means to cut in half. Perpendicular means a 90-degree angle, right? So how do you make a perpendicular bisector? It comes down to that vesica piscis, a fish bladder. Take a compass. In order to bisect something, you're taking a measurement. You're going to be using your compass. Make a circle of that length, of the length of the segment. Put it at one point. Go to the other side, do the same thing. We know those two circles intersect. Where do they intersect? Let's zoom out. Okay, I've got those two intersection points. This circle intersects that circle at those 2 points. I'm going to drop down a line. Dropping down a line. Where do they intersect? Right there. That I claim and argue is a perpendicular bisector. It cuts that segment of those two lines in half and makes a 90-degree angle. How do we find out? Let's measure between this, and this. It's indeed 90 degrees. Notice GeoGebra does the nice little square there because it's square. All right, so I've proven that it bisects it. Does it cut it in half? Let's measure. The length between here and here is 3.84. 3.84. Now, to show you that it doesn't matter, if I move any of these pieces, that still stays 90. It still bisects that regardless of the length or the position of that segment. So you can cut any segment in half at a 90-degree angle that will also, well, I just said it. You cut it in half and it's at a 90-degree angle. Enough said, I guess. I mean, that's the story. Again, by Tim. Any questions on that? If I can perpendicularly bisect something, I can now make an object that is very familiar to us as Masons. And let me actually do that. See if I can do that on the cuff right here. If I make a compass, pardon me, I'm going to take a line. I'm going to put a line through this. And I'm going to make another circle of that length. And, oh, it's actually not where it needs to be. I'm not going to do it freehand. That's actually dangerous. But you guys know what I'm going towards. I think you all see what I'm about to probably construct for us. Two parallel lines embodying a circle. And I'll show you how to construct that here in a little bit. It's easier to do with the parallel lines. Actually, let me go back to that parallel line construction. So doing a parallel line construction here to create the Masonic symbol that we're so familiar with. Again, take your line, put it through here. I'll do this very quickly, so bear with me. I need a point on an object. We'll put that point right there. Circle of this length. And again, circle of that length here. where do these two intersect? A compass of this length. Put that right here. And draw a line between here and that point. So those two lines are parallel, right? If I wanted to put a circle in between them, how about I drop a perpendicular? To drop a perpendicular, all I need to do is make a segment. If I put 2 points on a line, take 2 given points between these two parallel lines. Actually, pardon me, I did it. I want 2 points on a given line, and now I want to perpendicularly bisect it. Very easy to do. Take your compass, put one there, take your compass, put one there, put the line between the intersection of those two. Let me zoom out a little bit. Okay, I know that cuts it in half, and I'm going to do it one more time. I want to now cut, I want to do where this line intersects this line and this line intersects this line. If I want to perpendicularly bisect that, I can do the following. There's a line there, there's a line there. Making that fish bladder again, I know that that point right in here is the center of this line. So now all I need to do is make a circle. Oh wait, I gotta need that intersection point. I need a circle of that length, put right there. And believe it or not, that right there is your circle between, let me see if I can clean it up a little bit for you.
Looks like a crop circle.
It's crop, exactly. This is how the aliens do it, with crop circles. So you're gonna take this, and I'm gonna zoom out, and I'm gonna put that circle right on that line. And there you go, you made a circle with 2 parallel lines on the center. And if you don't like what that looks like, if you don't like its angle, go ahead and turn your piece of paper. So that's how you construct a circle of equidistant parallels with the 2 St. Johns. Now, let's talk a little bit more about construction of perpendiculars.
Question?
Go ahead, question, yes.
Yeah. When you were doing that, if you drew one circle and then take the point of the compass and draw a second circle from the rim of the first circle, if you just join up the outsides, you've done it.
That's true. That's another simple way of doing it. But you need to make sure that the line you're drawing is truly tangent to those 2 circles, right? And that's the tricky part. To do it with a compass and straight edge, to prove that it's tangent is more tricky than doing that construction of intersections and pieces like that. But you're absolutely right. If you could take your straight edge and say, yeah, that looks close enough, you could then absolutely make those tangents.
Masons are always close enough.
That's right, exactly. So let's do another perpendicular, but they want us to do a perpendicular through a given point, right? Now, how do we go about doing that? Again, it's measurements. So we're going to take a compass, and I'm going to make a circle of that length, and I'm going to take a measurement. So those of you who are playing at home, make a line and put a point anywhere on that piece of paper. Okay. And now what you're going to do is you're going to make a circle of the length from that dot to P and that dot to P, and they're going to intersect. And if you place them, if you drop a line between that, I should do some intersections so that we know what we're taking measures of. If you measure that, it will be 90 degrees. It's that simple. Okay, so if you're given a point off a line and you want to measure a 90-degree from it, just take your compass, make a circle of that diameter and a circle of that diameter. They will intersect in two places, and that will give you your perpendicular line. Any questions on that? Hearing none. What if I wanted to drop a perpendicular through a point already on a line? Oh, man, how do I do that? Well, that is a good question. There are a couple of ways of tackling this. So it doesn't matter where that point is on the line. But one way of doing it is the following. Make a circle of a given length on your compass. It doesn't have to be of a measured distance, just make a circle. And now that I have that circle, where does that circle, centered at point P, it has to be centered at that point, where does it intersect that line? In two places. I know how to do a perpendicular bisector, don't I? And I know that P is right smack dab in the middle. I just got to drop perpendicular on it. So I can do that by making a circle of diameter of the radius of that one. Saying where do they intersect? And dropping a line. Boom. And now let's prove it. Did I drop a perpendicular? I did. And what shape are we seeing again? It's this vesica piscis. And they called it that because supposedly pull a fish bladder out, it kind of has that shape. So if any of you go ice fishing this upcoming week in Maine, it's free ice fishing week here in Maine. So if you go ice fishing next week here in the great state of Maine and you get yourself a nice bass or a pickerel or something that's got a swim bladder and you take the swim bladder out, check to see if it looks like that. But that, again, is a very aesthetic shape in image that shows you how to drop a perpendicular down on a point on a given line. Okay. How are folks feeling? I'm going back to gallery view. I'm going to step back here. 1 through 5 again. 3s are like, 2's like, this is still good, brother. I saw somebody doing that. Good. I got some. How are we doing on the chat? How are people feeling there? 1 through 5s.
This kind of looks like an eyeball, that center construction.
It does kind of look like an eyeball. Those of you who are on the chatty, how are we feeling there? 1 through 5. What do we got? Chime in for me. I can't see.
So it looks like the alien crops I see on the farms.
Well, it's because they're easy to make, right? You guys could all go out into a field and make some of these crop circles, middle of the night. But good lodge activity. Go out as a lodge and start making crop circles, and I'm sure that will get the media's attention, and the conspiracy theories will go flying. So good. People are feeling good. I've got some 5s there. Wonderful. Okay, that helps us with an understanding of angles and lines and points. This is now leading us into the construction of regular polygons. I remember why I had this worksheet here for compass and straight edge construction. I wanted to give people the opportunity to try and create a point or a given point inside a circle bordered by 2 parallel lines. So actually, what I would like to do, looking at the time and seeing that we're pretty good on time, is I would like to give us 5 minutes for you to play around and try to do that. See if you can create that same construction that I had done earlier with a point within a circle bordered by 2 parallel lines. Okay, so see if you can do that. I'll give you 5 minutes and then we can try to share either on your camera or if you're on GeoGebra, I can go to this activity and share that screen as well. So try it on GeoGebra. If you're doing it on GeoGebra, try it on paper. See if you can construct that, which means no cheating, no being like, it looks tangent. See if you can construct it with the tools that we've given you. All right, so I'm going to give you 5 minutes. I'm going to mute myself. I'll check in 5. So that's 10:18, okay? I'm realizing I'm probably still sharing my screen. My way is not the only way. I'm just playing around. How are folks doing? We still got a couple minutes. Hope you're still playing around.
I tell you what, it's harder to do it longhand here with a actual square and straight edge and stuff than it is on that computer.
That's totally, absolutely true. I'm realizing that as well. But I get more satisfaction when I actually do have the compass and straight edge in front of me for whatever reason. The feel of the graphite on paper, it's got a good feel to it for whatever reason.
I've been doing it on the computer with you, but then I'm going to try it on the piece of paper here in front of me. It's harder on the piece of paper.
Oh, I bet. And so I'm just playing around with some of the colors so you can see where it lives within all those shapes. I think this construction. Oh, go ahead.
It's been a long time since I said it's been forever since I used my grafting tools.
Oh, but they're fun to use. So, yeah, this I tried to highlight it so you could see where the colors are and where it lies within that construction. And this construction actually is different than the one I had done previously. And so they're more than there are more than one pathway up this flight of winding stairs to get you where you may want to go.
Now
Anyone
you can do that pattern. That pattern goes on indefinitely, correct? Like
Yes.
you could make the same one pattern.
Absolutely, Brian. You could copy that over. You could make a whole chain of these, you know. I'm assuming that was Brian that I heard. Is that correct?
Yeah, Brian. Yeah. At no point does that change unless you change the angle, right, or the drawing. You know what I mean?
Right. The only thing I'm able to move right now is B, and that
Yeah.
just changes the.
So you could go on.
You could go on forever. You could make a whole necklace of these, so to speak. You could just chain it on indefinitely. So anyone want to share what they've constructed? I can go to the classroom and take a look. Hold on here. Let me get into the class.
Does it start changing if you start like going 3-dimensional with that pattern?
Ooh, when you get into 3 dimensions, certain Euclidean principles don't necessarily hold like you would think they would. But there are similarities.
Even if you draw it the same. Okay.
It depends if you're, because when you, hold on, my video's not on, so my hand motions, you can't even see what the heck I'm doing. Hold on. Okay. So if you're watching the screen, here's some hand motions for you. So Euclidean wise, oh, look at my dog Bandit decided to come to school with me. So Euclidean wise, you can do angles this way, right? And then when you go to 3 dimensions, the question is, are you rotating around this point? And you've got this another realm of rotation, or are you actually projecting up? It just adds a whole nother dimension where you've got to do some real careful thinking to make sure what you're claiming in 3-dimensional space is actually working, because there's a whole thing about packing or tiling 3-dimensional space that behaves differently than it would either in 1-dimensional space, which is just a line, or 2-dimensional space, which is a plane. I wish it was an easier answer, Brian.
No, that's okay. That was way advanced for me, so that's good.
Well, what we can do, if people are enjoying the geometry series, I can build off from this course and continue to explore things and head over in that direction. So, other questions? Anyone want to show off their construction? Those of you who have a piece of paper, if you want to put it up and show us, we can. If you want, no pressure. Oh, nice. Look at that. Very nice. You guys see that? That was brother. Oh, the names aren't coming up for me for whatever reason. No, that looks good. There you go. Anyone else want to show off their construction? Anybody on the classroom want me to go and click on their screen and bring it up? No takers? That's all right. Task 9. Look at Dan, you're knocking it out of the park. 7 out of 18 of the tasks completed. Oh, John is 8 out of. I've never seen this side of it, so it's fun to see. That's good stuff. Okay, let me go back to my my sheet here, and I think, if you don't mind, I'd like to move on to regular polygons. Everybody comfortable with that? Ooh, I see some chats. Are we good in the chat? No problem. Take care, Ranesh. Have a good night. So great to see him join us from India. So let's go to regular polygons now. Now, we're going to talk about a series of regular shapes: triangles, squares, hexagons, octagons, dodecagons, and you'll notice there is a trend, okay? Usually it has to do with doubling or cutting something in half, because that is a technique that we've learned how to do. So first, let me show you the equilateral triangle. Steve Phelps made this wonderful animation of how to make an equilateral triangle. Notice he does basically almost half a circle. same size, so you don't have to change the size of your compass. And he's making that bisectors, right? You have that fish bladder. And he's saying if you connect those intersections with that line, you will have made an equilateral triangle. So feel free to do that. If you're on GeoGebra and you're on the that construction page where you're just allowed to play, feel free to do that. Make two, give yourself a segment, make two circles. So you make the bisectors, take one of those intersection points, and using your straight edge, connect the dots. In the words of Pee Wee Herman, connect the dots, la, 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 if people are old enough to remember Pee Wee Herman. So yeah, so that's one of the easiest constructions right there, is to construct an equilateral triangle. Questions on that? Seeing none, let's talk about a square. So this is how you inscribe a square into a circle, right? A square is a regular polygon. Regular means same angles everywhere, same lengths everywhere. And we'll start back at the beginning. Again, this is an animation. This was an animation by Edward Note. He's got a couple of these. I want to make sure he gets credit for his hard work here. Going through these 12 steps, he starts with a point. He puts another point on the piece of paper, AB. He makes a circle of length AB. So if you're doing this at home, feel free to go ahead and do so. Or if you're on GeoGebra, feel free to do the same. He connects the points AB to a segment. He makes a line. He dots it so you know that it's not going to stick around, but he makes a line going all the way through. And I think that's so he can see the intersection point C. You're halfway there. Make a circle centered at C, and then make a circle of the same length around B. Notice that the circle has to be greater than A. It's past that midpoint. You could make them larger if you wanted and stick with the bisectors if that's what you're comfortable with, but it doesn't have to be that long. It just has to be beyond the midpoint. So he's made those two circles centered around C and around B. The next thing he's going to do is he's going to drop a line between where they intersect. Or first he's going to mark them. So mark D and mark E. And then drop a line in between them. I know that this line is perpendicular to CB. As a matter of fact, it's a perpendicular bisector of CB. Given that, he's going to mark where that new red line intersects the circle, G and F. And now that he has done that, all he has to do is connect those dots, F, B, G, and C. And when you connect those, you have now inscribed into the circle a perfect square, a polygon of 4 sides with their internal angles all measuring 90 degrees. Pretty cool. Now, from there, if you know the triangle, equilateral triangle, and you know the square, it won't be very hard to do a hexagon or an octagon, and we'll show you how. First, any questions on this? Everybody feeling okay? Okay. The regular hexagon. If I wanted to create a regular hexagon, there are a couple ways of doing it. I want to make sure I don't do the way that's going to be shown here. Oh, whoops. I guess I can't get to that one. So let me show you how to do a regular hexagon by starting with a with an equilateral triangle. So to do an equilateral triangle, I will take a compass. And again, I like to use the Visica Piscis myself. And what I'm going to do is I know that this is an equilateral triangle. Okay? Now, if I bisect, if I want to do a perpendicular bisector, to these different areas, I can do so by, again, finding where certain things intersect. For example, I know if I intersect these two and I drop a line between here, or a segment, pardon me, I'm going to do a segment between G and H. I know it bisects the triangle here. If I do the intersection between this circle and this circle, and I make a segment from here to here, I know it bisects this one. And now I need to bisect this one, this side right here. And in order to do that, again, I can go and I can make a circle of the same length here. And which one am I missing? Oh no, I already have it. Pardon me, I already have it. If I do the intersection between this circle and this circle, I now know that between here and here bisects this side, okay? Now, interesting question. Where is the hexagon? Well, the hexagon is actually between, let me do the intersection point there. If I were to make a circle of this length, let me change the, can I change the color on it? If I've got this little circle in here, where these lines intersect with that circle is where your hexagon will be. So between, I'm making those points right now. And now, if I were to do a polygon between here and here and here and here and there and here and here and here, I now have a hexagon. I took my triangle, I cut it in half, it gave me a regular six-sided shape. Questions on that?
You're only one line away from a pentagram too at one point.
You are, but the angles are the tricky part. Because the angle, in order to create the internal angle of a pentagon, you need the golden ratio. And so we need to learn how to construct the golden ratio, which will be a different class. Now I'm going to show you something else. There's another easier way to do it that I think you guys will find fascinating. So I showed you the hard way, constructing from a triangle. Now let me show you this way. I'm going to create a circle of the same length, and I'm going to continue to create the same length circle, and I'm going to march it around the original circle. So I got that rusty compass. The circle's got the radius the same as the same radius all the way around. And what I have created is what is called in some circles the seed of life. You see this seed right here in the middle? That's called the seed of life. If I take all those points where these circles that I walked around the first circle, if I connect them all together, what do I get? Starts with an X. Boom, we nailed it. See, just told me right there, we nailed it. That gives you a hexagon. So that's the other way to create a hexagon. Questions or thoughts on that construction? That one's a lot easier than trying to cut up your triangle, isn't it?
It's interesting how you start to see organic symmetry too, the more complicated it gets.
Absolutely. Absolutely. This, believe it or not, if you take this seed of life and you superimpose over it the two St. John's paralleling a circle, is my master's mark in the York Rite. So if you have not gone through the York Rite, that is one of the degrees, and you get the opportunity to create your own mark. Mine is this. Any questions on this?
Oh, you could get a bigger hexagon by connecting the intersections on the outside with circles, right?
Ooh, that's a good question. Because I'm not certain, I actually am going to test that hypothesis. I think you're correct, but let's find out. Let me zoom out here. Can I zoom out at all? Hold on. No, it won't let me zoom out, but I think you are right. I'll have to try it on a different piece. You'd have 1, 2, 3, 4, 5, 6. Actually, 1, 2, 3, 4, 5. Yeah, I think you would. And then you could just make hexagons all the way down. What about the regular octagon? He creates 2 dots, creates a circle of that length, creates a line through those 2 green points. Finds the other intersection. See, he put that one right there. Creates a bigger circle of diameter, the diameter of the smaller circle. Looks like the Death Star. Creates another big circle. There's your fish, your Visica piscis. From there, he marks the intersection points here and here. He drops his vertical, perpendicularly bisecting it. Then what's he do? He says, where do those intersect? And he makes a square. To make the octagon, he's going to use the similar strategy we used previously, which was to bisect those edges. How is he going to do that? He's going to do that by making 2 circles and another Visicus piscis to cut this other one in half. So he cuts it in half. He'll do the same thing on the other end to cut that in half. Now that he's cut that in half, he says, where does it intersect the yellow line? You see them as green dots now on your screen. Maybe I can actually, there you go. That's probably easier for you to see. He makes them green dots on his screen, and then he connects them to make a stop sign. And that's how you create the regular octagon. Does the hexagon one work on yours as well? It does. And that just shows, yes, he's just walking through the same way to make the hexagon, to show you that other method that we had done previously. What about the dodecagon construction? A dodecagon, do is 2, deca is 10, 2 and 10. You're looking at a 12-sided shape. Start with a point, make another point. And again, if you're playing at home, feel free to play along. Make a circle. Make a second circle, same length. Look, what he's doing now is he's making the hexagon using that method that we saw earlier by making the seed of life. Now, this is interesting. He drops a line in between the two little seeds, if you were like, if it was like a cucumber and you cut it in half and those are your seeds inside your seed pod, he connects alternating seeds. And he'll do that again. Alternating seeds get connected. Alternating seeds get connected. Alternating seeds get connected. I'm going to say this before it's your mantra. You're going to say it to yourself as you're taking your nap this afternoon. Alternate seeds get connected. Alternate seeds get connected. So he's connected all those alternative seeds. What does he do next? He finds out, okay, where did those intersect with the bigger circles outside? He's using those parallel lines that he drew to mark all those spots. So he's going all the way around and marking where the parallel lines intersect with those outer circles. Now that he's done that, there's your hexagon, your dodecagon. Your dodecagon is out here. And there's your 12-sided shape. So that's how doubling and halving can allow you to create shapes of 3, 6, 12, 24, 48, though they start looking like circles unless you have a really big piece of paper, or 4, 8, 16, 32. Those are regular shapes you can now construct at the end of this class using the tools and skills that we have learned and discussed today. Any questions on these constructions before I show you some further resources and open it up for us to do some closing discussion and just dialogue on things that we were able to take away and to give me feedback on how to improve this course, as it was really kind of an experiment that I'm very glad you all came along with me on. Any questions on the constructions?
Can I ask one quick question, Luke?
Yes.
You know, obviously this starts to remind me of fractals at some point.
Yes.
Computer generated, I would call it art. Fractals to me is actually a form of art, geometric art.
I'd agree.
But basically all a fractal is continuing this in a visual form ad infinitum, right?
Yes. What you're looking for in fractals is they're self-similar, which means if you zoom into a fractal, you get the same picture back, right? That can happen in geometry. I think it was it Brother Brian that was saying this, where you could keep doing this out ad infinitum, and it's got this transitional symmetry. You can move the paper and it looks just like it looked like before you left it. In some sense, it's a tiling of the two-dimensional space. And yes, so there is some self-symmetry. With fractals, that self-symmetry tends to come in through zooming. And so there are ways you could create a fractal in doing this by zooming in and recreating the construction you just made, zooming into the same spot, recreating that construction, and keep zooming in like that. You would be able to create some type of fractal type pattern in doing that. And it has to do with that zooming or that either the expansion or contraction of that shape. Great question, Dan. Other questions? This is good. We can do the dialogue now and I can show you the further resources at the end, actually. Other thoughts?
One quick question to follow that up then.
Sure.
It's almost like, so if a fractal is a repeating pattern, essentially, and we're looking at this pattern right now, the dodecagon, which is not necessarily a repeating pattern, or is it a repeating pattern? Because, you know, my question is can math have a finished sentence where if you look at a dodecagon, it is a sentence that's done because it will not repeat anymore after this? Does that make sense?
Yes. And in geometry, you can, in some aspects, you can create a quote unquote finished sentence. And usually what happens is you have to actually create irrational numbers. We haven't talked about irrational numbers. It's one of the things we usually talk about a little bit in the in-person class that's about 3 hours long. it gives us another hour to talk about special angles and irrational numbers and rational numbers, because when you deal with irrational numbers, you sometimes don't run into these patterns that you can be like, oh, I just do this again and do this again, because the square root of 2 behaves in a very strange way. It never repeats. It goes on forever. You can't write it as a fraction, which prevents you from having some of that fractal type behavior in geometric constructions, because you are limited to only a compass that measures a distance in a straight edge. And there are certain things that can't be constructed. You cannot square a circle. Using a compass and a square edge, you cannot create a square that has the same area as a circle. You can't do it. It's been proven. You cannot make a cube through compass and straight edge construction, like building the sides and everything, with a volume of root 2 or something like that. So there are certain things you can't do. There are certain equations you can't solve. There is a branch of mathematics that takes geometry and road maps it over into algebra. And what we call transcendental numbers, like pi and e, cannot be constructed. You cannot map out pi with a compass. You can't measure out pi, which is weird because pi is in circles everywhere. The circumference of your circle is 2 pi. You know, areas of your circles involve pi, but there's no way to measure out on your compass pi. It's transcendental. It transcends the ability to create it geometrically. There are so many interesting things in mathematics that I'm excited to potentially produce more mathematical topics that venture into the realm of philosophy or different size infinities or things like that. If that's something that that would be of interest to brothers and for the Maine Masonic College to do. So great questions. Other ones? Oh, it looks like we have some in the chat.
Yeah, John says his head's exploding.
Ah, that's why I fell in love with math, John, because my head exploded when I finally understood that there were different size infinities. Some infinities are bigger than others. We won't get into that in the next 10 minutes, but it's just amazing the realm.
Please don't. I think you've done enough damage already.
Ah, wonderful. So other thoughts or comments. Let me actually just show the resources so you at least have them on your screen, and then I'll take the other thoughts and comments. So you should see here this is still on Dan's. Let me go to this one right here. My profile. It's in the book I made, Introduction to Geometry. Further resources. Here's some further geometric light. GeoGebra, this is just the link to the website you're using. If you do want to play around with it and you like mind puzzles, Euclidia is an app for your phone that the levels are you have to like bisect something or copy this angle, or can you do something in so many moves. It really is a lot of fun. I have it on my phone. It helps keep me sharp. It's a fun game to play. It's called Euclidia, construction games for your phone. Then I'm not sure if this gentleman is a Mason or not. His YouTube channel is called Sacred Geometry Decoded. And he has a couple videos in there that I think you may find interesting. If you are interested in the Knights Templar and the Seed of Life, he has a video in here. He's got 24 different or 40 different videos where he does, 19 videos where he does constructions with music in the background. And one of them is he makes a Templar clock from the Seed of Life. And so if you want, you can go to his webpage and view those, listen to some music, and just kind of enjoy the beauty of the geometry. And then for those of you who like to delve into the mathematics of it, Math Open Reference constructions do step-by-step constructions. So if you were confused by any of the constructions we did today, this resource right here, Math Open Reference constructions, will give you the opportunity to go and follow them step by step on your own time. So there is just some resources for you to continue your geometric exploration. With that, I'll go back to the chat and we'll have some more conversation as we start winding down in the last 10 minutes here. Brian, glad you made some more coffee. Keep you going. Yes, pie not square, pie or round. Unless you go to a church dinner and it's in a casserole dish, then you can get some chicken pot pies that are pretty square. Any other?
It's just amazing how they.
Yes,
it's just amazing how they use this back in, like, you know, of course, the beginning of masonry. It's just phenomenal.
Yeah, it's amazing what mathematics opens up to the world. They say, you know, physics and science, you can describe the world around you, but mathematics is truly queen of the sciences. Without her, what you can't measure, you can't deduce, you can't use logic, you can't develop argument, rhetoric, the things that are on the winding stairs on the journey that we are on. Arithmetic and geometry, it's like that lecture. It really is the basis of charting out the stars, of music and tempo, of art. If you got to see our course on the secret geometry of art, it's in there. It's just, it's wild. And I love it.
It would have been cool to live back during those times and see how they were, you know, discovering all that.
Absolutely. Because the math they're discovering now, it's so specialized. You have to get, it's so cerebral and like alien, some of the math that they're talking about now. I wonder if back in the day when they were discovering these things, if those thoughts and ideas were as alien to them. The idea of an irrational number, that you could not write a number as a ratio. I believe people have actually died claiming that irrational numbers are actually irrational. Transcendental numbers. What do you mean there's a number I can't construct? I can at least construct square root of 2, which is irrational. I mean, I bet those things were blowing people's minds, you know? Sorry, I'm talking a lot, and really this is your course. So feedback from you and thoughts from you is wonderful. I'll mute myself and be quiet for a bit.
Luke, thanks for a very interesting course. Anybody have some stuff you'd like to see added? I know Luke was talking about expanding into other courses. So a couple ideas of where you'd kind of like that to go. I mean, I know myself, I'm interested in mass, and that's only because from my perspective as an artist, being able to represent, you know, mass took such a long time for the artistic world to figure out how to do. But mathematically, it's fascinating too, to go from, you know, like you were saying, the points to the lines to the superficies to all of a sudden having mass. And that's a huge leap also. Anybody else have some thoughts about things mathematically you might be curious about?
And I will try to make it as digestible as possible. Like if people wanted to understand how different size infinities works, I can try to break that down into digestible chunks.
Whoa. Different size infinities?
Yeah, it's crazy. The guy you want to check out is what is his name? It's a C. I'm looking right at him. It has to do with Cantor. His name is Cantor. You want to look up a mathematician named Cantor, Cantor. He talks about the different size infinities. I could talk about non-Euclidean geometry. I could take it to the next level and we could just do a simple course on constructing the pentagon in the square, the golden ratio. That may be a fun one. But again, we're here to bring more light to things that you would like to see. And feedback on the course would be helpful as well. How did this work out? I know usually we're all in person. We all have compasses and straight edges and all that, but we had to improvise here. And I'm curious to how that worked out as well. I see a thumbs up there that it seemed to work well. Some other thumbs up. Good.
Yeah, that online tool was really good. That made a big difference for me.
I'm glad it helped. Thank you. Thank you, brothers.
I think it makes a big difference when you shared it, you know, so we all could get on the website and use that. That was neat. And I think maybe if we were all together in a large dining room, we wouldn't have that capability. So it was great to have that.
I got a question, Luke.
Yes.
Would you help me construct something up in Chuck McKay's field this summer?
Oh my gosh, is that Pat Holt? It is.
Yes.
I didn't even know. Uh-oh. If I knew you were on here, I'd be a little more careful with what I was saying. Pat's a big friend of my family. Nice to see you, Brother Holt. Sure, I'll help you construct
too.
that.
Yeah, we could do a crop circle. That would get some attention.
Let's do that. Let's go out back in Tupper's farm. We'll just make a whole bunch of crop circles and see what
That's
happens.
what I'm talking about.
Everything that was done today can be done with a piece of string out there. Other than
Exactly.
the compasses. Yeah.
Exactly. Get some yarn and have somebody sit in the middle of the field while someone else starts walking around in the cornfield.
Which the Egyptian did to remark out their fields after each flood, the large distances, and knotted string, you know, not 3 feet out, not another beyond that 4 feet, another 5 feet. You get a right angle and so forth. You, our ancient brethren did a lot with very few tools. Well, our angles too, that we were talking about the angle of the degrees in an angle. That's based on their counting system, the Persian counting system on their knuckles, because we have 3 joints in each finger, so they could count to 12 on one hand. And by using 2 hands, 5 times that 12 is 60. And that gives us our 60 degrees in the equilateral triangle, etc. So that's why our master looks toward the east. All right, I'll shut up now.
No, that's great.
All right, well, we're winding down on our time. Any last questions from anybody before we go?
Just a big thank you.
This morning.
You're all very welcome.
Thank you so much.
You're very welcome. Take care,
Thank you.
everybody.
Appreciate it.